if you were to look at kind of the main topics that you would want to make sure you cover in a calculus class, this is one of them. Every single calculus class, whether it be a short calc or a survey of calc or AP calc or CIS calc, they'll all cover this topic. And it refers to your first and second derivative tests. We are going to learn about what the derivatives tell us about the graphs. And so let's start right here by looking at this graph. Is the derivative of this graph positive or negative right here? Okay. So here's what we say. If the derivative is positive, the function is increasing. If the derivative is negative, the function is decreasing. If the derivative is 0, then there might be a local min or max. For example, if I had a graph like this, the derivative is equal to 0 right here at this spot, yet it's not a local max or min. So you're not guaranteed to have a local max or min, but you might. So let's look at these spots. As we move to the top, it says increasing, we take the first derivative, and we look at where it's greater than 0. For decreasing, we look at the first derivative, and we look at where it's negative or less than 0. For local maxes and mins, we take f prime of x and set it equal to 0. So we can make this statement. If there is a local max or min, then the derivative will be equal to 0. But we may not say, if the derivative is 0, then there's a local max or min. We cannot make that statement. Second derivative test is different, and this is something that you conceptually need to understand. I would say that this is probably the most important concept for the day for you guys to really kind of get into your brains. All right. So I'm going to draw a series of tangent lines. Would you agree that these tangent lines are all, until I get to the 0 one, that before that they're all positive? You tell me what's happening to the tip on the right hand side, the tip of those tangent lines. It's dropping, isn't it? In fact, this tangent line, does it have a very positive value or a somewhat positive value? Very positive, right? It's very steep. Yet right here on this one, it's just somewhat positive, right? So you can see that it's the degree to which it's increasing is starting to decrease. The tangent line is actually starting to drop. In fact, does it continue to drop after that? Yeah, I need a volunteer. Kimball, you tell me, when does this tangent line, when will it stop dropping and start to tilt back up? Okay, you tell me when I get to the spot. Nope. I'll draw some more tangent lines, folks. See if we can get it. Is the tip still continuing to drop lower? Is it still continuing to drop lower? Is it still continuing to drop lower? But now, what's happening to the tip? Now, the tip is moving up, isn't it? Look at all these derivatives. Okay? Look at the tip. It's dropping down. Okay? Look at it. I'll circle them. See how they're dropping? Whoop. And then once it gets to here, it starts to tilt back up, right? This is the most negative that the derivative ever gets. Would you agree? At this spot right here, somewhere around here, this is the most derivative or most negative that the derivative ever becomes. Okay? So, the derivative, is the derivative positive or negative at this spot? It's positive. However, is the derivative increasing or decreasing at this spot? The derivative is moving towards a decreasing state. Is the derivative positive or negative at this spot? Negative. But is the derivative increasing or decreasing at this spot? It's increasing. Okay? That's important. That's what we call the second derivative. Look at this spot right here. This spot where that changes is called the inflection point. Behind it, we have this sort of a graph. This is concave down. Then we have this sort of a graph. This is concave up. The second derivative, where it's equal to 0, divides the graph into two spots. A portion where it's concave down and a portion where it's concave up. So concavity and inflection are two new concepts that we learned today. Concave up is where f double prime of x is positive. So you can see from my graph, this second part here, the tangent lines were starting to tilt up. So that's where it's concave up. It would hold water. If f double prime of x is less than 0, if the derivative is decreasing, it would dump out water. And it's concave down. The inflection point is where f double prime of x changes sign. That often is where f double prime of x is equal to 0. Okay? So when you see if f double prime of x is equal to 0, you got to make sure that changes from positive to negative in between. Then it's an inflection point. Here's an example of a double derivative that's equal to 0 that does not have an inflection point. If we look at y equals x to the 4th, anybody know what that graph looks like? If I had a bunch of other stuff with it, like x to the 3rd, x squared, and you know, other stuff, then it would be a w. But just like this, it basically looks like a parabola. It's just flatter on the bottom compared to x squared. What is the first derivative? And the second derivative, okay, first derivative tells us where it's increasing, decreasing, where I might have local max and local mins. If you were to take 4x to the 3rd and set it equal to 0, where would x be equal to 0? At x equals 0. So, do I have a local min at that spot? Yeah, I do. Take the second derivative, set it equals 0. That happens at x equals 0. So you might say, well, you have an inflection point there. Well, isn't this thing always concave up? Yeah. So you can see you don't change inflection. It's always concave up. Okay. So that's something you have to consider. So, and we'll try many of these examples. You will not have an assignment tonight. We won't get through enough notes, but we do want to finish this piece off. Here's another thing that's very important. Local max. This spot right here, local max or local min? Local max, is it concave up or concave down? So a local max occurs when f prime of x equals 0 and f double prime of x is less than 0. So if the second derivative is negative and the first derivative is equal to 0, then you know it's a local max. Local max or min? Min, concave up or concave down? Concave up. So therefore, if f prime of x is equal to 0 and f double prime of x is greater than 0, then you know you have a local minimum. Here's what I like to do. I like to make number lines. I make one for the first derivative, I make one for the second derivative, and I put it above and below the graph. Would you agree that f prime of x is equal to 0 at approximately right there? Which is at an x value of about negative 2.7? And would you agree that f prime of x is equal to 0 at about 0.8? Can somebody choose a value between negative 2.7 and 0.8? 0. What do you think the value is of the first derivative at 0? Do you think it's positive or negative? Because the function is decreasing. So you're right, you get a negative value there, you get a positive value here, and a positive value here. That way I can see the intervals on which it's increasing and decreasing. Then when I look at the second derivative, it looks like at approximately x equals negative 1, it has a second derivative equal to 0. If you plug in a value to the left of negative 1, say negative 5, do you think you come up with a positive or negative value for the second derivative? Negative. Why? Because it's concave down. And on this side, it's concave up, so you get positive. And so when I do my number line tests, because I won't have a graph, I will try to sketch a graph once I have this information. That's what I do. So let's do one example together. We'll be done for the day. Okay, I take the first derivative, f prime of x. I want to be able to identify intervals of increasing, decreasing, concavity, and local maximum and inflection points. What is f prime of x equal to? Would you agree that that's x minus 2 times x plus 2? So I make a number line. So it's equal to 0 at negative 2 and at positive 2. Let's do some number line testing. What's the number to the left of negative 2? Sure, or negative 3. Negative 3 minus 2 is negative. Negative 3 plus 2 is negative. Negative times a negative is a positive. So am I increasing or decreasing? What's the value between negative 2 and 2? Negative times a positive is a value to the right of 2. 3 minus 2 is positive. 3 plus 2 is positive. Positive times a positive is positive. So therefore, I know my intervals of increasing and decreasing where I might have local maxes and local mins. Let's do the second derivative. F double prime of x is equal to 2x. Let's draw a number line. Solve that equal to 0. 0. Plug in a number to the left of 0, negative 1. You get positive or negative. Number to the right. So you can see what it tells us about the graph. Let's label all the important spots. Increasing. What intervals is it increasing? Negative infinity to negative 2. Union with 2 to infinity. What interval is it decreasing? Negative 2 to 2. Concave up. What interval? 0 to infinity. Concave down. A local max is where the derivative is equal to 0 and it's concave down. Where is the derivative equal to 0 and it's concave down? -2, the derivative is 0 and it's concave down. So -2 is where you have a local max. Let's find the y value for your local maxes and mins. How do you find the y value? Plug it in, and you get -8/3, +8, so +24/3, +2, which is 6/3, 22/3. You're going to have to do that arithmetic on your calculator or some way. A local min, yes. A local min happens where the derivative is equal to 0 and it's concave up. Where's the derivative equal to 0 and it's concave up? At 2. Plug in 2 and we get 8/3 minus 24/3 plus 6/3, -16, -10. So that was at 2 and -10/3. Finally, an inflection point occurs when the second derivative is equal to 0 and you have a sign change. Where is the second derivative equal to 0? At 0. Is there a sign change at 0? Does it change from positive to negative? It does change from positive to negative. So therefore we have an inflection point. Find the y value by plugging 0 in and you get 2. That's class. No assignment, but be ready for a long assignment tomorrow. Have a good day.